thanks for tuning into this Revision Zone Maths video. In this video, we're going to be calculating partial fraction forms of regular fractions. So let's get started. So the natural place to start is to basically ask, what is it, right? The answer to that is generally we go from sort of some sort of fraction, or say a list of fractions. So we might have, like a over b plus c over d, and then we might want to go to something which combines them in a form whereby we can, in this case, we can sort of write down ad plus bc over bd. The process of partial fractions is actually reversing this process. So it's starting with something which looks a lot more sort of simplified in one way, combined, to actually going back to getting individual fractions that you would have had to have added to be able to get that upon combining these. Okay, so that's what it is. Now the next question might be, why do we actually need partial fractions? And the answer is, well, it's like algebra. Because algebraic re-expressions of statements are terribly important, they give us a lot more flexibility in being able to express ourselves, then partial fractions basically just add to that toolkit. But in a more precise way with regards to the A-level syllabus, partial fractions allow us to integrate certain functions. Okay? Now, a third question would be, well, how do we work out partial fractions? And the answer is, well, we will see lots of examples in the video. See examples. I could go into generic theoretical description of this sort of thing, but I think it's just a lot more beneficial to see a few examples and then see it for yourself how this works. So let's move on to that. So example one requires us to express this fraction in partial fraction form. So let's see a solution. So I want to be able to rewrite this fraction 5 over x plus 1 over x plus x minus 4, sorry, in some sort of a form such that when I combine the things on the right-hand side, I'm going to get the fraction on the left-hand side. Okay? Now, it's not going to be surprising that with fractions, the denominators are most important, because as long as we have a common denominator, then the numerators can just be added. So, given that I'm going to have two separate fractions, I want to make sure my denominators are going to be consistent. So the denominators have to basically be this, right? And at this stage, for now, we can just say it's a guess. I can just say there are going to be some numbers, a and b, at the top, such that I have two fractions. The first one is a over x plus 1, and the second one is b over x minus 4, such that when I combine them by getting a common denominator, provided I make the right choices for a and b, I'm going to get the same thing as the thing on the left-hand side. Now, why exactly this form works, that's a much longer discussion, and perhaps we can have this later on in the video. But for now, let's just work through this in a systematic way. So I have my right-hand side. I'm just wanting to now undo the fact that I've written them as separate fractions and combine them, and then use some algebra to be able to work out the values for a and b. So I want to get a common denominator. So the common denominator is going to be obviously x plus 1, x minus 4. So I multiply the top and bottom of the fraction on the left by x minus 4, and the top and bottom of the fraction here by x plus 1. So it's going to be plus b over x minus 4 times by x plus 1. So since the denominators are now common, I can basically combine the numerators. So I can just say a x minus 4 plus b x plus 1. The whole thing is actually over x plus 1 x minus 4. Okay, and at this stage we can simplify this further by sort of expanding out the things in the numerator. So I get ax minus 4a plus bx plus b. And again, the denominators are precisely what we had before. So lastly, at this stage, we just got to collect our terms. So I can collect the two x terms. So I can say a plus b x plus it's going to be b minus 4a. Okay, that's the constant term. So x plus 1, x minus 4. Now, this is the important step. So we've got to now a form where we've recombined our initial expression to have one fraction, but that one fraction obviously has to be equal to that. In fact, not just equal, it's got to be identical. It means it's true for every single conceivable value of x. So what we can do is we can just equate coefficients. So we can say equating coefficients, right? So another way of doing that is you might say, well, you multiply, perhaps I can rewrite this in a slightly better way. You can say we can multiply both sides of the sort of this equality here by the denominator, and I can end up with something like this, which is 5 is equivalent to a plus bx plus b minus 4a. So since I have that, we can equate coefficients. So equating coefficients of say x, I can say, well, on the left-hand side, there is an x term, which is 0 times x, right? So a plus b has to be equal to 0 because there's a 0 times x here. So a plus b equals 0. And then equating the coefficient of the constant term, which is x to the power 0 term, I can say that 5 better be the same as for a b minus 4a. So we've got b minus 4a is actually equal to 5. Now, at this stage, we solve these simultaneously. So I can say my a plus b tells me actually my a is actually minus b. And then that tells me that actually my b minus 4a is the same thing as b minus 4 times by minus b, because a is minus b. And that's equal to 5. Well, that is the same thing as 5b, sorry, 5b. 5b is equal to 5, and that of course tells me that b is actually equal to 1, and since b is equal to 1, I don't know why I've written 5 down, since b is equal to 1, then that tells us, going back to the statement a equals minus b, that tells us a is actually equal to minus 1. So we've actually worked out our values for a and b. It's worth having a quick check, so let me just make a bit more room and then we can carry on. In the interest of time, I've written some of the answers out already. So we've already seen that 5 over x plus 1 over x minus 4 can be expressed in this way in partial fraction form, and we've worked out that actually if that's the case, then a has to be minus 1 and b has to be 1. And so we've basically claimed that this identity is true, right? So the check would be, well, let me combine this on the right-hand side and show that it is indeed going to give me the left-hand side, and that's what we've done here. So as always, because we have two fractions with different denominators, we want to combine them so we get a common denominator by cross multiplying. So I multiply the top and bottom of that by x minus 4. We see that here, and I multiply the top and bottom of that by x plus 1, and we see that here. So just simplifying this, obviously the minus 1 is going to go into the bracket to give me minus x plus 4, and then the 1 is just not going to do anything to the x plus 1, so I'm just going to get that. And then we just combine the numerators, so I get minus x plus 4 plus x plus 1, and obviously the plus and minus x cancel, and the 4 and 1 combine to give me 5, and the common denominator is obviously x plus 1 over, sorry, x plus 1 times by x minus 4. So indeed, we've actually been able to show that our partial fraction form worked, right? And now this is going to be the sort of useful thing. If we actually had to integrate this thing here, which is 5 over x plus 1 x minus 4 dx. As it stands, this is actually very hard to integrate, but if we had to integrate this thing on the right-hand side instead, this is actually very, very easy to integrate. I won't go into the integration here, but I hope from just this statement here, you can actually see already the value that partial fraction actually brings. Okay, so let's look at the next example. So example 2, we're given another expression that we have to basically write in partial fraction form. So let's jump straight in. So we want to write 6x minus 2 over x minus 3 times by x plus 1 in partial fraction form. And of course, the partial fraction form is going to be determined by the denominators. So I'm going to write down a over x minus 3 plus b over x plus 1. Okay, because when I combine something like the thing I've written on the right hand side, I have some hope of getting something that looks like on the left-hand side, because the a times by that denominator is going to give me a linear function, and the b times by that denominator is also going to give me a linear function, and so the two linear functions in the numerator are going to combine to give me a linear function. And of course here I have a linear function, but then the denominator, by having a common fraction, is going to be a factorized quadratic, so that looks reasonably sensible. So again, as we did last time, let's just combine this. I'll do it sort of slightly faster. And of course, I've already described what it is I'm doing, which is combining the right-hand side to get a simplified fraction, so I can then sort of equate it to the left-hand side. Expanding the numerator here, I get ax plus a, and then the other one gives me bx minus 3b. Uh, and then the denominator is obviously the same. And then at this stage, we can collect terms. So the ax plus bx is just going to give me a plus b all times by x, and then the a minus 3b is just going to give me a minus 3b like this. And at this stage, we can basically say, as a result of this, then we know, because the left-hand side has always just remained 6x minus 2 over x minus 3x plus 1, we can just say we better have 6x minus 2 being identical to a plus b times by x plus a minus 3b. Okay, so now, because it's an identity, we can equate coefficients, and we can say, well, we can equate the coefficients of the x terms. And what does that tell me? That tells me everything in front of the x here has to be equal to everything in front of the x here. So in other words, a plus b actually has to be 6. And let's label that equation 1. And in the second case, everything that's here, the constant term, has to be the same thing as everything that's there. So the one thing I've got to worry about is there's a plus here and there's a minus here. So indeed, if I really wanted to be technical, I could have rewritten this as 6x plus minus 2x to the 0, and I could have rewritten this as x to the 0 here, right? So we're really equating x to the 0 terms. So we can say a minus 3b is actually equal to minus 2, and that's just a direct comparison of the coefficients, as I've already said. So at this stage, we want to actually solve the equation simultaneously, and we can just do 1 take away 2. And when we do 1 take away 2, the left-hand side just basically gives us a minus a is going to give us 0. So no a's, that's the whole point of doing the taking away. And then b minus 3b is just going to give us 4b. So the left-hand side becomes 4b, and the right-hand side becomes 6 minus 2, which is obviously just plus 8. And then that gives us a value for b, so b equals 8 divided by 4, which is just 2. And since I have a value for b, I go back to my equation 1, then I can say 1 actually implies that a is 6 minus b, which actually is 4. So we've managed to solve this, and we can indeed say that 6x minus 2 over x plus 1, or x minus 3x plus 1 rather. It doesn't really matter if I change the order there, because multiplication is commutative, but let me just write it in the same way that we've been writing this down, is actually going to be identical to 4 over x minus 3 plus 2 over x plus 1. And of course, it's worth just checking this very quickly. So I've just written down the answer we got, and let's just combine this. Of course, we want a common denominator, so I'm going to multiply the fraction on the left by top and bottom by x plus 1, and the other one top and bottom by x minus 3. So I'm just going to say 2x minus 3, and then we have a common denominator. So I've done multiple steps in one go, because we should be comfortable with this sort of thing at this stage. And of course, the top then gives me 4x plus 4 plus 2x minus 6, and then the denominator is x minus 3, x plus 1, and unsurprisingly, the 4x and the 2x combine to give me the 6x, and the 4 minus 6 is actually minus 2. So indeed, the answer we worked out is the right partial fraction form. So let's move on to the next example. So for example 3, we've got something a tad bit more complicated than some of the things we've seen so far. The complexity comes from the fact that there are now 3 factors in the denominator, okay? Which just means that when we unpack this into sort of expression as a partial fraction, we're going to get 3 separate fractions that we, one of them is going to have denominator x minus 2, the other one's going to have x plus 6, and the third is going to have x plus 3. So let's see that. So we want to express 7 over x minus 2 x plus 6, x plus 3 as a partial fraction. So again, as I've already said, it's going to be something over x minus 2 plus something over x plus 6, and then something over x plus 3, and we have to figure out what these somethings have to be in order to make this work. So as always, we just want to combine this. I'm going to try and do it instead of one step. We see we have an x minus 2 already here. So to get that denominator, I've got to multiply top and bottom of this by x plus 6 and x plus 3. So I'll do that instead of one step. X plus 6, x plus 3. And then for the second term, we've already got an x plus 6 in the denominator. So to be able to get that denominator, I've got to multiply top and bottom by x minus 2 and x plus 6. So the b is going to come with the x minus 2 and the x plus 3, sorry. And then lastly, the c has an x plus 3 in the denominator, so I've got to multiply top and bottom by x plus 6 and x minus 2. So I'm going to say plus c, x plus 6, and x minus 2. And of course, the whole point in doing this is once I've done this, I'm going to have a common denominator of x minus 2, x plus 6, x plus 3. Now, at this stage, from what we've done in the past, we would expand this out, get a quadratic, and then equate coefficients. And we can do that, and that would completely work. However, that's not the easiest way of doing it. Nevertheless, because this is the first time we're sort of seeing something as complicated as this, it's worth doing it just to see what it comes out as, and then maybe I can go over and sort of explain the other way of doing it as well. So I've just got to be able to expand each one of these quadratics. So the first one's going to give me x squared plus 3x plus 6x plus 18. And the second one's going to give me, obviously the b's on the outside, it's going to give me x squared plus 3x minus 2x minus 6. And the third one's going to give me x squared minus 2x plus 6x minus 12. And the denominator obviously is the same. It's just x minus 2, x plus 6, x plus 3. But at this stage, I really do need to collect my terms. So let me perhaps do that here. So what does that give me? That gives me x squared. The 3 and the 6 is going to give me 9x plus 18. And perhaps I can change color. So this one here is going to give me x squared, and the 3 and the minus 2 is just going to give me an x. Minus 6, and then lastly let me perhaps take red, and I can do that here. So I'm going to get x squared, and the minus 2 and the plus 6 is actually going to give me a 4, and then the minus 12 is just there. So now here comes the big step of actually combining things and collecting terms in terms of x squared. So I see I've got an ax squared, I'm going to have a bx squared, and I'm going to have a cx squared. So actually my x squared term is going to be a plus b plus c x squared. And then I see that my x term is going to be a times 9, so it's going to be 9a. And then I'm going to have a b times 1, so I'm just going to have a b. And then also I'm going to have a c times 4, so I'm actually going to have a 4c plus 4c, and all these are my x terms. And then finally I'm going to have my constant terms, and that's going to be a times 18, so that's going to be 18a. So let me write that here, 18a. And then my second term is going to be b times by minus 6. So perhaps I need a negative there. I need a negative 6b. And then lastly, I'm going to have a c times by negative 12. So I actually need a negative 12c on the side here. Okay, so at this stage, what we then need to do is, given that the left-hand side, and I will write this out actually, given how horrible the thing on the right-hand side might look to some, and they might not be able to follow what I'm doing. So I'll write this out. So given that we know the left-hand side is 7 over x minus 2 x plus 6 times by x plus 3, we can multiply through by the denominator and basically end up with something like 7 is identical to a plus b plus c x squared plus 9a plus b plus 4c x plus 18a minus 6b minus 12c. Okay, and this is where we now start to equate coefficients. So let me say equating coefficients. Again, because the left-hand side has 0x squared terms, I can just say a plus b plus c actually has to be 0, and that's my first equation, right? Then the left-hand side here has no x terms, so 9a plus b plus 4c has to also be 0, right? Because I could, as I've said sort of before, I could actually rewrite the left-hand side as 0x squared plus 0x plus 7. So I'm just equating coefficients. So I can sort of come back and say the second equation I get is going to be 9a, not 98, sorry, 9a plus b plus 4c equals 0, and this is equation 2. And the third equation I'm going to get is, of course, by saying actually then all that constant part better be 7. So I'm actually going to get 18a minus 6b minus 12c is equal to 7, and that's my equation 3. And at this stage, we need to basically go away and solve these, and that's going to be a fair bit of work. I don't think it's worth actually getting into here, so I'll just write down the answers. So upon solving these simultaneous equations, we actually find that A is 7 over 40, B is 7 over 24, and C is minus 7 over 15. Of course, do feel free to check this for yourself, either by solving these equations yourself, or by putting the answers back into this form and then combining to see you do get 7 over x minus 2x plus 6x times 3. So here's the alternative approach. We again start with the exact same thing, and the partial fraction form generally is going to be the same. And as before, we just combine it by getting a common denominator and by multiplying top and bottom of this by x plus 6, x plus 3, multiplying top and bottom of this by x minus 2, x plus 3, and multiplying top and bottom of this by x minus 2, x plus 6. So that's quite clear. However, at this stage, we don't actually expand. What we say is we just multiply through by this denominator here, but obviously because that denominator is common to both sides, we end up with this identity. So a times by x plus 6 times by x plus 3, and then b times by x minus 2 times by x plus 3, and c times by x minus 2 times by x plus 6. And the beauty of this is, because this is an identity, this is true for all value of x, right? Since the above is an identity, it is true for all values of x. Now, I can just basically pick values of x, put it in, and then solve, right? But I'm going to pick my values of x very, very strategically. So I see that if I pick an x equals 2, then this term here goes away because the x minus 2 becomes 0, and then it doesn't matter what these numbers are, the whole thing just becomes 0. And of course, if I pick 2, then x minus 2 comes here as well. That means x minus 2 here goes to 0, so the whole thing here goes to 0. So actually, I say take x equals 2, and what that actually tells me is the left-hand side is obviously going to be 7, but the right-hand side is going to be a times by, well, 6 plus 2 is 8, and 2 plus 3 is 5. But then the other one gives me b times by 0 times by, well, it doesn't even matter what it is, but let's just write it down, 5. And then it's going to be c times by 0 times by, again, I'm going to get 8, but obviously this entire thing is 0, and this entire thing is 0. So actually what I have is I have 7 is actually equal to 8 times 5, which is 40. So I can just write down my value for a straight away. So a is 7 over 40. And this is precisely what I said was the answer in the in the previous case. So now to work out the values for b and c, we again just pick strategic values of x so that the calculation becomes easy. And I can see from here, because I want to keep my b, I don't want to pick -2 or -3, so I've got to pick something else. But look, there's a x plus 6 here and there's an x plus 6 there. So if I pick a -6, this does not go to 0, but that goes to 0 and that goes to 0. So I'll just say take x equals -6, take x equals -6. Then the left-hand side of my identity above still just remains 7 because it's independent of x, but the right-hand side actually becomes a times by 0 times by -3 plus b times by -6 minus 2 is -8 times by -6 plus 3 is -3 plus c times by -6 minus 2 is -8 and then times by 0. And again, as before, this thing here goes to 0 entirely, and this thing here goes to 0 entirely. And so the left-hand side, or the right-hand side rather, in this case, becomes 8 times 3, or -8 times -3, which is actually 8, 16, 24. So 24b, and that tells me b is actually equal to 7 over 24. And this is precisely what we worked out in the previous case. So again, we can repeat this entire thing. We can say take x equals, and we see that a -3 here and a -3 here would make these things go to 0, but there's no impact of that on the term on the right hand side. And you can actually figure out you can figure out value of c. I won't do that here, but of course, if you do the calculation, then c actually turns out to be exactly what we said last time, which is -7 over 15. So I hope you would agree that this method of reasoning is a lot nicer to use when we've got more complicated expressions for partial fractions, and we can sort of eliminate things a lot more easily as opposed to getting lots of simultaneous equations and doing lots of algebra and then having to work the answers out. So example 4, we again have something which sort of makes things a little bit more complicated. We now see that our denominator is actually a squared. So just off the bat, I would like to say you might think to yourself that a good way of tackling this would be, say, to express the squared as two separate things, and then to treat them as sort of two separate things, to be able to say a over x minus 5 plus b over x plus 3 plus c over x plus 3. But actually, this turns out not to be a good way of doing this, and the reason for it is it should be pretty clear immediately, because there is a common denominator here. So the minute you write it in this form, it's exactly the same algebraically as writing it in this form. So I can just do this plus d over x plus c, x plus 3, sorry. So you see, so here, clearly I hope you would agree that this is not a suitable form of partial fraction if we want something of that form. How do I know that? Well, straight away, because if I combine the denominators, I get a quadratic, whereas here I have a cubic, and that alone is problematic. And of course, algebraically, having these two terms as separate is exactly the same as just having one term here with a different numerator. So we need to be careful how we write down our general description of partial fraction before we start doing any algebra. Let me make a bit of room and then we can get started on this problem. So the more common way of doing this is actually, obviously, we start with the fraction that we want to express in partial form, and then we do write down the a over x minus 5. But then this term here, the x plus 3 squared, we actually want to express that in a slightly more generic form. We want to express it as x plus 3 plus c over x plus 3 squared, right? And now we don't run into the problem that we ran into last time. So as always, we combine all the denominators, and in this case, I've got an x minus 5 here, so I've got to multiply top and bottom by. I don't have to do that and that because there's a common factor here. So I can just multiply the top and bottom of this by x plus 3 squared. So I'll just do a x plus 3 all squared. And of course, why have I done that? Because the minute I multiply top and bottom of a over x minus 5 by x plus 3 all squared, the denominator is just going to be x minus 5 times by x plus 3 all squared, right? So now going to the second term here, I want to multiply top and bottom of this by x minus 5 and 1 factor of x plus 3. So I'm going to say b x minus 5 and 1 factor of x plus 3. That would guarantee that this fraction here has the same denominator as x minus 5 times by x plus 3 all squared. And lastly, the c, the only top and bottom multiplication needed is by x minus 5, and that would give me the right denominator. So once I've got it in that form, I'm not going to expand and sort of collect terms. I'm just going to say this just tells me that 2x plus 9 has to be equivalent to everything in the numerator. So the two numerators are equivalent. So I'm going to get a x plus 3 squared plus b x minus 5 times by x plus 3 plus c x minus 5. And at this stage, we're going to say we're going to pick values of x strategically to try and evaluate and work out values of a, b, and c. So I'll say take x equals, let's say minus 3, because the minute I take minus 3, then that goes away and that goes away. So I'm just going to quickly write down that gives me 2 times minus 3 plus 9 is actually equals a times by 0 plus b times by 0. I don't really care what else is there. Plus c times by minus 3 minus 5, which of course upon simplifying gives me on the left hand side minus 6 plus 9, which is, and the right hand side just gives me minus 8c, which tells me my c is actually minus 3 over 8. So now we go back to this statement, and now I can pick an x equals 5 because that would kill the b and it would also kill the c, leaving me with the a. So I say take x equals 5, and when I take x equals 5, I basically get 2 times 5, which is obviously 10, plus 9. So that's the left-hand side just gives me 19, but the right-hand side gives me a times by 5 plus 3 is 8 squared. And then obviously the other ones are just going to give me 0. That's the entire purpose in choosing 5. So I actually get 64a is equal to 19, which tells me a is actually 19 over 64. So we've worked out our a. And now here we run into a bit of difficulty because of the fact that we've got a repeated factor here, we can't choose a third number to kill the other term. So we've already got b and sorry, c and a. I can't pick any number to just sort of get rid of a and c and just leave me with b. So what I'm going to do, I'm just going to pick one nice number, and I quite like 0, so I'm just going to take x to be 0. So I'm going to put x equals 0 into this entire equation. So 2 times 0 is just 0, plus 9 is 9, so the left-hand side just becomes 9. The first term on the right-hand side, 0 plus 3 is just 0, so that squared is just 9, so I'm going to get 9a. And then the second term is minus 5 times by 3, which is obviously minus 15, so I'm going to get minus 15b. And then the third term is just going to be 0 take away 5, is just minus 5, so it's just going to be minus 5c. So we already have values for A and for C. So of course we can just actually use this equation to say that actually my B is going to be, if I sort of do it all in one step, it's going to be 9A, take away 5C, take away 9, and the whole thing is going to be divided by 15, obviously, right? And you can work this out. It gives minus 19 over 64. So at this stage, I would encourage you to sort of go away and check maybe that the values for A, B, and C that we've worked out, once we put them into the sort of initial expression we found and we combine, we actually do end up getting the thing on the left-hand side. Okay, so these values of A, B, and C will give us the right partial fraction expansion. So example 5, we're given another function, and in this case we're again asked to express that as a partial fraction, and we see we have two factors in our denominator. I should say at this stage that this factor here is a quadratic factor, so you might think that you'd be able to factorize it. In fact, this is not possible to factorize this within the reals. So let's work out a solution. So we want to start with 2x squared plus x plus 8, and we want that to be over 2x minus 1 times by x squared plus 2, right? And because we want to write it as a partial fraction, we want the denominators to be the things we have on the left. So we're definitely going to have that, okay? and we're going to have x squared plus 2. Now, in the past, we've just come here and said an a and a b. And the reason why we've said that was because every time in the past, we've had the thing on the top on the left-hand side of the numerator has been a linear function. So if we just have a and b here, then obviously when we cross multiply, we get linear terms, and then that's sort of okay. But in this case, we don't quite have a linear function. We have a quadratic function. Now you might say, hang on, I've got a quadratic here, so when I cross multiply, I should be able to get a quadratic, and so that should be fine. And let's try that. So we simply say we cross multiply, so we say that, and then b times by 2x minus 1, and then the whole thing is obviously over 2x minus 1 times by x squared plus 2. And at this stage, we can do the sort of thing we've been doing, which is we can say 2x squared plus x plus 8 is actually identical to a x squared plus 2 plus b 2x minus 1. And already you should be able to see that there's actually a big problem here. The reason for the problem is there are three coefficients here, and even though I'm going to get three coefficients coming out of this, there's only two unknowns. So that tells me the thing I've written down in that form is actually not general enough. Okay, so we can work this out and actually just convince ourselves that this is not going to work. Let me just expand this to say ax squared plus 2a plus 2bx minus b, and obviously that's the same thing as ax squared, and then combined the b term is just 2bx, and then the last term is just 2a minus b. And I'm going to equate coefficients because that seems very easy here. Coefficients, what we actually get is when we equate the coefficients of x squared, we get 2 equals a. When we equate the coefficients of x, we get 1 equals 2b. So that tells us b is actually equal to a half. And when we equate the coefficients of x to 0, we actually get 8 is equal to 2a minus b. But the point is we already have values for a and b, right? So if I put these in, then what I'm going to get is I'm going to get 2 times by 2, and then the b is just minus a half, so it's just going to be 4 minus a half, which is 3.5, and here we have a problem because 3.5 is not equal to 8, okay? And my equation tells me that it actually is. So that's exactly making the point, which is what I said, which is, in fact, what we wrote down initially is not good enough. So this is perhaps what some people say is the hardest part of partial fractions, which is knowing what sort of thing to write down here on the right-hand side before you start doing all the manipulations. And I will give you a description of what sort of heuristics you've got to have in mind when you're writing this sort of thing down. The general idea is the thing you write down has to be general enough so that when you combine it, you can get something on the left-hand side. Okay? And provided you write down something that's general enough, that's always going to work. And how can we guarantee that the thing that we write down is actually general enough? So there's a basic rule, and the rule is each partial fraction must be of form, and here's the form. It has to be of order n minus 1 over order n. Okay? So if you've got something of order n at the bottom, so this is of order 2, the top has to be of order 1. And in this case, we don't have this of order 1. Currently, that's just of order 0. Right? That's currently order 0, and that's what's causing the problem. This is completely fine because we've got order 1 here, and that's order 0, and 1 and 0 is less than 1, but this one is not fine. So perhaps what I'll do is I'll tidy some of this up and then reattempt the question in a slightly better way. So having tidied some of the things on the screen, I now come back to the exact same thing that I had, and rather than writing something on the numerator for this term, which is of order 0, I write it something which is of order 1. So I'm going to say bx plus c, okay? And then we just proceed as we actually had done in the past. So we just combine things to have a common denominator, and then we say bx plus c is going to be multiplied by, of course, 2x minus 1. and then the whole thing is over 2x minus 1 times by x squared plus 2. So at this stage, we could substitute values in by equating numerators or actually equating coefficients. But because I did the last part of this by equating coefficients, I'll carry on and just sort of equate coefficients. So I say 2x squared plus x plus 8 is actually going to be equal to a x squared plus 2 plus bx plus c, and that's going to be times by 2x minus 1. And then just tidying things up, I can say ax squared plus 2a plus bx, sorry, 2bx plus 2cx minus bx minus c. Okay, so collecting terms, we can say a plus 2b has the x squared term and the 2c minus b, that's my x term, and then I have 2a minus c, that's my constant term. And already you can see there's a lot more flexibility here. When we got this sort of an equation last time, this identity last time, there were only two unknowns in that, but now there are three unknowns here, and of course there are three coefficients to be equated, and life in that way works out to be a lot nicer. So equating the coefficients, we say of x squared, we actually get 2 is equal to a plus 2b. And of x, we actually get 1 is equal to 2c minus b. And of x to the naught, we actually get 8 is equal to 2a minus c. So we can solve this if I label these 1, 2, and 1, 2, and 3. I basically take my 1 and 2. I basically say 1 plus 2 times by 2. And what does that give me? Well, the left-hand side is just going to give me 2 plus 2, but the right-hand side is going to give me a plus 4c, and of course the 2b here and the negative b times by 2 added are going to cancel, so I'm just going to have no b's. And this is precisely why we did this, because now we actually have, I should have said that's equation 4, now we actually have equation 4 which we can solve with equation 3. So equation 4 tells me that actually a is equal to 4 minus 4c, and then that can be put into equation 3, and equation 3 becomes 8 is equal to 2 multiplied by 4 minus 4c minus c, which of course tells me 8 is equal to 8 minus 8c minus c, which tells me c is in fact 0. So I get 8 is equal to 8 minus 9c, but obviously that tells me c is 0. So we've worked out the value for c. Since we know what c is, we can also work out what a is. So we use the fact that a is equal to 4c minus c, but c is of course 0. Well, that straight away tells me a has to be 4. So perhaps I can sort of write that down on the side in a different color. So let me say answers. So we know our c is 0 and we know our a is 4. So now that we know c and a, I can actually come back to any one of these equations and work out what b is. So from here, this might be easiest. So c is 0, so our 1 is actually minus b, which means b is minus 1. So b equals minus 1. So we've been able to work out our partial fraction. Let us quickly check our answers just to make sure we didn't make a mistake. Of course, the partial fraction we were trying to work out was something of that form, and we know what a, b, and c are. So I'm just going to put that in. So I'm just going to say 4 over 2x minus 1, and then b is obviously minus 1, so it's going to be minus 1 times x, and the c is 0. So actually, I just get that, which can be written in a much nicer way as 4 over 2x minus 1 minus x over x squared plus 2. So all we want to do is we want to actually combine the thing on the right hand side and then show that it's the same thing that we were trying to simplify initially. Okay, so again, common denominator, so I'm going to multiply the left by x squared over x squared plus 2. Let's write that down, and then the left, the other thing is going to be 2x minus 1 is going to be multiplied top and bottom, so x is going to be multiplied by 2x minus 1. So now that we have a common denominator, well, this is just going to give me 4x squared plus 8, and it's going to be take away 2x squared plus x, okay? And then the denominator is just going to be 2x minus 1, and then x squared plus 2. And now, just simplifying the numerator, the 4x squared minus 2x squared is going to give me 2x squared, and then the plus x is just going to be there, and then the plus 8 is going to be there. And the denominator is, of course, 2x minus 1, x squared plus 2. Indeed, you can go back and check. This is precisely the fraction that we wanted to express in partial fraction form, and we reasoned our way to be able to say the partial fraction must be of this sort of form and worked out a, b, and c, and we've just shown that doing the calculation, the a, b, and c we worked out are actually indeed correct. So I hope you found this useful. With that, I'd like to end the video. Thank you for watching. If there are any comments you have with regards to what you would like for us to make more videos on, do let us know in the comments section. Hit the like and subscribe buttons, and we will see you in the next video.